Section 5.2 builds on the idea of solving systems of equations in two variables. This time, we're going to have systems of equations in three variables, x comma y's comma z's. If there's three variables, we're going to need three equations at a time to solve them. Two equations, two variables, three equations, three variables. One equation, one variable. The solution to a system of linear equations is no longer just a coordinate point x comma y because it's a place in 3D space, which means it's going to be an ordered triple x comma y comma z. So our first step in working with these systems is being able to verify that our answers, after we've done all this glorious amount of arithmetic and algebra, is correct. So what we're going to do on just this problem right here is we're going to take the ordered triple -1, 2, -2 as the x, the y, and the z. And we're going to plug them into the system of equations we were given to just verify that it's a solution. I'm giving you ways to check your work here. But what we would be doing is we would be plugging the x, y, and z into that first equation. So that would be -1 plus 2 times 2 minus 3 times -2. And we're hoping when we do this arithmetic that it equals to 9. And again, all I did was put the x where the x goes, y where the y goes, z where the z goes. We'll do this with our brain. I know you have a calculator, but let's do some mental math here. 2 times 2 is 4, so this is going to be -1 plus 4, and then -3 times -2 is +6. I want to add the 4 and 6 first because that's nice and pretty and it makes 10. So then this equation becomes -1 plus 10, which is like 10 minus 1. That means it's 9. That's exactly what we wanted because equation 1, when we plug in the x, the y, and the z, should have given us 9. And that's what we got. We plug the values into the second and the third equation as well. So this next one is going to be 2 times -1 minus 2 plus 2 times -2. We're hoping it's going to be equal to -8 when we've done all of this arithmetic. 2 times -1 is -2, and then 2 times -2 is -4. -2 minus 2 minus 4. Is that -8? Sweet. It has to work in all three equations, so we're almost there to verify that this is a solution to the three variable system. We would do negative times -1 plus 3 times 2 minus 4 times -2. -1 is +1. 3 times 2 is 6. -4 times -2 is +8. 1 plus 6 is 7. 7 plus 8 is 15. Is that what we wanted? If we get check marks on all three, that means we've checked the ordered triple x, y, z in all parts of this system of equations. That ordered triple, that place in 3D space, is the location where the planes that represent these different things intersect. Cool? Now, how do we actually go from being given the equations and solving them? That's a great question. You'll notice on the back page, you have a lot of space, yes? Use your nice handwriting, please. When we're solving a system of equation in three variables, we're only going to be using the concepts that we learned last time from elimination to do this. When we were doing elimination, for something to eliminate, what had to happen on that variable? Like the numbers in front of the variable, what did they have to be? Cancel outable, meaning what? One of them positive, one of them negative, and the number being exactly the same, correct? So that's our goal here, is we're going to want to reduce the system into two equations with two variables. We're going to want to eliminate one of the variables from two different pairs of equations, but making sure we eliminate the same variable from both pairs. When we're done with that, we will have a two-variable system with two equations, which means we can solve. We go back to the steps we learned last class. Once we have a single number, like x equal to 5, we take that number and we back substitute by plugging it in. We get another variable, and we plug it in again. We get the ordered triple. Are you ready to see this process from start to finish? You're shaking your head no, but we're doing it anyway. We're going to first start by making sure we have all letters on the left side of the equation and single numbers or constants on the right side. Are we good? Check. We're going to label them equation 1, equation 2, equation 3. This becomes very important when we start making these steps to know what we've done to what equation. Now I'm going to pick the z's to be the thing I want to cancel out. Looking specifically, don't circle this because you'll get annoyed later. Looking specifically at the z's, why do you think I want to cancel out the z's here? Yeah, they're like multiples of each other, yes? And one of them's already positive, one of them's already negative. If I want them to have the same exact coefficient but opposite signs, what would I multiply this by to make it positive 4? 2, because this would be negative 4z, this one would be positive 4z. So what I'm going to do is I'm going to take the entire second equation and I'm going to multiply that second equation by 2. So I show my work like this. I'm saying I'm taking equation 1 with no change, so 5x minus 2y minus 4z equal to 3. And I'm taking the second equation, but I'm going to multiply everything by the number 2. This becomes 6x plus 6y plus 4z equal to negative 6. Yes, you even multiply it times the number on the other side of the equal sign. Have I lost anybody? Why did I choose to multiply by 2 again? Yeah, we want something to cancel, yes? And we see that if we multiply by 2, they end up being the same. Okay, so we go ahead and add these two equations together. We end up with 11x plus 8y canceled equal to negative 3. How many variables are left here? You're so right. That's so embarrassing. What should that be? 4. Correct. I did that on purpose. Okay, we've written a new equation. When we did this with 2 variables, we are already to the point where we could solve for a particular number. We still have 2 unknown values here. We're going to label this equation 4 because we've just made a new equation. Now we go back to the original question. I either need to combine equation number 1 and 3 or equation number 2 and 3 in some way to make the z's cancel. But we're going to pause right here because I know we're thinking about food and we're about to go to lunch. Look at 1 and 3 or 2 and 3 to see if you can eliminate something or what you would need to multiply by to eliminate the z's specifically. Okay, if we're committing to 2 and 3, here's going to be equation 2, here's going to be equation 3. Would they cancel immediately if I just added their z's together? No. What would I have to multiply each of them by to make that happen? Say again? 2 by negative 2, that would make it negative 4z and then the 3z. Do they cancel yet? Oh, by negative 3. My bad. Didn't hear you. Negative 3. Let's try that. So if I do negative 3 times the second one, yes. This would end up being negative 9x minus 9y minus 6z equal to positive 9. Okay, so now I have it as negative 6z. What do I need to multiply number 3 by to make that one positive 6z? 2. So I'll multiply 2 times equation 3. This becomes negative 4x, bless you, plus 10y plus 6z equal to 6. Now again, we chose this because it's a different, unique pair, and it's still canceling out the z's, which is what we canceled out the first time. When we add these two equations together, we end up with negative 13x plus 1y, cancel out the z's, equal to 15. We have now made the 5th equation in this problem. But what do you notice about the 4th and the 5th equation that we've made? They don't have a z, but what letters do they have? X and y. They are now a 2-variable system. 2 variables, 2 equations we can solve. We're going to repeat the steps we just did. This time, we're going to do something to equation 4 and add that something to equation 5, or maybe do something in equation 5 as well, to make another letter out of 4 and 5 disappear. Do any letters immediately cancel if I were to add these two together? No, but is any of your spidey senses going off on maybe what we should do?
Switch negative 13x to the other side so it equals y.
Oh, I see what you're saying. So she was thinking of solving by substitution. You totally can. I want to stick with elimination here just so we get practice with elimination, but you totally can add the 13x to the other side so that's y equal y equal to 15 plus 13x, substitute it in and solve. Yes, great, definitely, especially if that's what your brain saw, do that. But if we're trying to stick with elimination, multiply the fifth equation by just 4? Negative 4. Because if we multiply the fifth equation by negative 4, here's what it would look like. We'd have 11x plus 4y equal to negative 3. And we'd have 52x minus 4y equal to negative 60. If we add these two equations together, we get 63x, cancel out the y's, equal to negative 63. Do you see the light at the end of the tunnel? What is x equal to? Negative 1. Hooray, but don't box it, because that's not the final answer. Remember, we're trying to find an ordered triple that represents the place in 3D space that these three planes intersect. We have one of the coordinate points. What we're going to do now is we're going to back substitute this in to one of the two variable equations, so number 4 or number 5, so that we can get another variable value. So let's take the x and let's plug it in. What would you like to plug it into, number 4 or number 5? I heard both. It truly doesn't matter. 5 was, somebody yelled that one louder. Great. We'll take x and we'll plug it into 5. So if we take x and plug it into 5, this is negative 13 times negative 1 plus y equal to 15, which would be 13 plus y equal to 15. So what is y equal to? 2. Hooray! We have 2 of the 3 pieces of this ordered pair. Ordered triple, sorry. The next step, the last step, is to back substitute the x and the y that we found into one of the original equations that has all 3 variables. Which one would y'all like to plug it into? Number 1, number 2, or number 3? 2. Sure. Said with confidence. I like it. We'll plug x and y into number 2, which means we're going to have 3 times negative 1 plus 3 times 2 plus 2 times z equal to negative 3. One variable, one equation. We can solve this. It's negative 3 plus 6 plus 2z equal to negative 3. Or if you condense negative 3 and 6 together, that's 3 plus 2z equal to negative 3. Subtract 3 from both sides. That's 2z equal to negative 6. Or z equal to negative 3. Which means that the ordered trio, the ordered triple solution to this system is negative 1, comma 2, comma negative 3. That's the x, comma y, comma z that solves this system. Whoa. Now, especially because we took a pause for lunch in the middle of this problem, let's look back from start to finish, and if there's any time something appeared on the screen that you're like, where'd that come from? Stop me and ask a question. When we started, we checked to make sure it was all variables on the left side of the equal sign and your constants on the right. Check. Labeled them 1, 2, 3. Why did I do this first? That's a good question, isn't it? So really, and here's where it comes down to, and I had good questions last class about this. You get to choose whether you're eliminating the x's, the y's, and the z's. And no matter which one you start with, it should work. Why do you think I chose to eliminate the z's out of these two equations first? They are in the same multiple family. There's a least common multiple amongst them. Yeah, we can see that it would be pretty easy to multiply just one of them by something to make it eliminate. So I multiplied 2 times the second equation, everything. I added the two equations together using the elimination method, and pow, the z's are gone. That's equation 4. Now, because I eliminated the z's, I have to eliminate the z's out of a different pair. It doesn't matter which pair, if it's 1 or 3 or 2 or 3, it has to be a different pair, and it has to eliminate the z's. So I multiplied equation 2 by negative 3 and equation 3 by 2 so that the z's would cancel out, and we get equation 5. From there, you can either use substitution to solve like we did in two variable systems, totally works, Or you look for another thing that will eliminate. This is my personal method of solving these larger systems. So we multiplied -4 times that fifth equation, so the y's would cancel out, and then we can find the value of the x. We back substitute that into either equation 4 or 5, one of the simpler equations, to get the other variable y. And then we back substitute the x and the y into one of the original equations that included the z, so that we can solve for z. Questions, comments, concerns? Fabulous. Let's try one more, shall we? When we start each of these problems, we're looking for a 3-variable system where all the variables are on the left side of the equal sign and all the constants are on the right. Are we good? To have all numbers on one side and all variables on the other? It technically does, but what do you notice about the first one, which is why I think some of you are telling me no? It has no which one? Oh, so the y has technically already been eliminated out of that equation. That is a hint for you. When you label these 1, 2, and 3, you're going to want to eliminate the y value out of equation 2 and equation 3 because it's already gone in equation 1. So if we're focusing on equation 2 and equation 3 to make something, the y's, disappear, what would I multiply these equations by to make the y's disappear? 2 by -2. If I multiply -2 by that second equation, I end up with -2x minus 2y minus 4z equal to -34. Do we follow that step when I'm distributing that scalar to everything? If I write down the third equation, it's x plus y plus 2z. I'm writing down the wrong one. Hello? X plus 2y plus z, my bad, equal to 16. When I add these two together, I end up with a new equation, the fourth equation in this problem, of -x minus 3z equal to -18. This is my fourth equation. Now again, I specifically chose to eliminate the y's here because if you compare equation 1 with equation 4, there's only 2 variables and they have the same variables, right? That's our 2-variable system that we now solve. And what do you also notice about the x's here and here? They're already opposites that are going to cancel. This is super nice and super easy. So in this question now, we're going to do equation 1 and equation 4. No changes. They're already going to eliminate something. So we would have x plus z equal to 8 and -x minus 3z equal to -18. When you add these bad boys together, your x's are going to cancel out. We have z plus -3z, which is -2z, equal to -10. Divide by -2 on both sides, we get that z is equal to 5. Look at that, we already found one of the values of this ordered triple because we were smart enough to look ahead and see what had already been eliminated, and we were able to skip some steps. So what we do now is we back substitute. We're going to back substitute this into one of the equations that only uses x's and z's. Would you like to plug it into number 1 or number 4? 1. Great, love it. Which means we're going to do x plus 5 equal to 8. I'm going to move mine down one. I didn't mean to write it that close. Sorry. So z into 1. So this is x plus 5 equal to 8. Which means what is x equal to? 3. Okay, we have 2 of the 3 pieces. Now we're going to take the 2 values we know, which is x and z, and we're going to back substitute them into one of the original equations that has all of the letters. The only 2 in the original equation that have all of the variables are number 2 and number 3. Which one would you like to plug it into? Sure. So we're going to take x and z and we're going to plug it into equation 2, which means we're going to do 3 plus y plus 2 times 5 equal to 17. That's 3 plus y plus 10 equal to 17, or y plus 13 equal to 17. So what is y equal to? 4. which means we found the ordered triple that solves this system, and that ordered triple is 3, 4, 5. We could take that x, y, and z and plug them back in with our calculator to verify, like we did on the front page, that that solution to the system is correct. Yeah, if you notice, we're already at the end, yes? This topic just requires time. So that's what I'm going to give you today in classes. You have a significant amount of time to work on the practice problems. If you did not do the notes for 5.1 over the long weekend, go back and do that. If you did and you're ready to start the 5.2 homework, I would start working on it now so you can ask me questions, ask your peers questions as you're working, because you have the entire rest of the class to work on this.